This lesson is going to examine the elimination method for solving systems of equations. So, like the substitution lesson, I'm going to start off with a couple of basic addition and subtraction computations. 13 plus 3 equals 16, and 5 minus 3 equals 2. Those are both true, and what I'm going to do with them is show you that if I add them vertically, I'll still maintain the equality. So let me show you what I mean. So I have three columns here, column 1, 2, and 3. I'm going to add them vertically. 13 plus 5 equals 18. Plus 3, so a positive 3 plus a negative 3 make 0. So there's nothing here. And then 16 plus 2 equals 18. The numbers changed. Something got eliminated right here, but did the equality stay the same? Did it maintain? Yes, it did. It's still equal when I add the columns in that fashion. Well, I can take this idea and apply it to systems of equations. So if I had something along the lines of three x plus 2y equals 12, and 3x minus 2y equals 24. Well, what I want to do is find the value of x and y that make both of these equations true. Well, similar to the previous computation, I'm going to create three columns and add them and see what happens. Well, 3x plus 3x equals 6x. 2y plus a negative 2y, similar to the previous computation, that cancels. So there's nothing there. And 12 plus 24 equals 36. Okay, so what that did for us is made this calculation and finding x much easier. Now what we have is 6x equals 36. So to solve for x, of course, we would divide both sides by 6, and x equals 6. Now that I know x equals 6, I can go back to either of these two equations, take my x equals 6, and plug it in right here and solve for y, or I could plug it in right here and solve for y. It doesn't really matter which one I pick. Just to follow through and finish this example, I'll pick the top one right here. So, I know x equals 6. So I'm going to erase this on the bottom to give myself a little room. So using this top equation right here, 3, and then in parentheses, I know x equals 6. I'm going to put 6. Plus 2y equals 12. Well, 3 times 6 is 18. Now, to start to get y by itself, I'm going to subtract 18 from both sides. This will cancel right here. And 12 minus 18 is negative 6. And then finally, divide both sides by 2, and I'm left with y equals negative 3. So my official answer as an ordered pair is 6, -3. that's the x and y that would make both of these equations true. Right, so what we did was we added vertically, and we were able to eliminate one of the variables and solve for the other one, and then go back and plug it in to find the last variable. Right? But what happens if they're not set up to cancel right away, one of the variables? Let's see what that case looks like. Okay, so let's say I had something like this right here. If I add these together just like I did in the previous problem, 4x plus 2x equals 6x, but now I have 4 plus a negative 2. Well, 4 plus negative 2 is 2y, and then I would have 20 over here. The only problem with that is we didn't eliminate a variable. So it's kind of hard to find a value for x when we have two variables with one equation. We could find an infinite number of solutions, but we couldn't narrow down the x and then therefore the y that would eventually make both of these true. We need to eliminate one so that we can either then solve for x, or if we eliminated x, then solve for y. It doesn't matter which variable you eliminate at first and then find initially. You just have to make sure you do the correct mathematical procedure to eliminate one of them. So, with that said, one thing we could do is, as we've talked about many times, as long as we do the same thing to one side of the equation that we do to the other, we still maintain the balance. We still maintain the equality. So what I could do, actually, is multiply both the top and bottom, or I'm sorry, the entire bottom, both left and right, of the equation by 2. So I'm going to distribute 2 everywhere. Here, here, and here as well. So, what that gives me is 2 times 2 is 4x. 2 times a negative 2 is a negative 4y. And then 2 times 4 is 8. Now what I'm going to do is bring this first equation right underneath my new equation. Okay, now I'm in a position that when I add these together, I can eliminate a variable. 4x plus 4x equals 8x, but when I add these, I get nothing, 0, and then when I add over here, I get 24. Now that makes things much easier. 8x equals 24. How do I solve for that? By dividing both sides by 8, and therefore x equals 3. So then what I could do is go back to either equation and plug in x equals 3 and solve for y. So if I take x equals 3 right here, I'm going to put it in right there. 4 times 3 is 12. And then 12 plus what would equal 16? Well, 12 plus 4 is what would equal 16. So therefore, y must be 1. Because 4 times 1 is what would give me 4. But I'm running out of space, so if you want to try that on your own, plug in 3 for x and then go ahead and solve for y, you'll find that y equals 1. If we tried it over here, 2 times 3 is 6. If I plugged in 3 for x, I would get 6. If I plug in 1 for y, 2 times 1 here is 2. And is 6 minus 2 4? Yes, it is. That's a check mark, so it fits both of them. So notice there may be certain times when you have to multiply either the top, the bottom, or possibly both, which I'll show you here in a second, to make sure you eliminate one of the variables. Okay? If you don't have a variable set to eliminate right away when you add both equations, check the smaller number and see if it goes into the larger number of the other equation. So over here, 2 goes into 4 and 2 goes into 4. So we could have eliminated x or y. But since y had already opposite signs, eliminating y became easier. Let's look at one more example. Okay, 5x plus 6y equals 35, 4x plus 7y equals 42. The problem right now is that 4 does not go into 5, and 6 does not go into 7, so we don't have an easy way that we can just multiply one of the equations by a particular number and get one of the variables to line up and eliminate. So if you're in a situation like this, you can pick either x and y and multiply by the other coefficient, or in other words, the other number in front of the variable, and make sure one is positive and one is negative. So let me show you what I mean by using x. I'm going to eliminate x. So the way I can do that and make sure I land on the same number is if I multiply 5 by 4, and if I multiply 4 by 5, I will end up with the same number. They both be 20x. Then the only thing that we need to make sure we do is make sure one is negative and one is positive. It doesn't matter which one we do, so I might pick this one at the top. Maybe 4 is a lower number than 5, but it doesn't really matter. So now, if I multiply through, I'm going to get a new top equation that is I just multiplied 5 through to each number. I got negative 20x minus 24y equals negative 140. Down here I'm going to multiply by 5. Five times 4 is 20, 5 times 7 is 35, and 5 times 42 is 210. So what that did for us is it lined up the 20s to have the same number with one being positive and the other being negative, therefore putting us in a position to eliminate, getting down to one variable and then solving for the others. So here this is going to eliminate 35 minus 24, or in other words, negative 24 plus 35 is 11y. and then negative 40 plus 210 is 70, and we could then go on from there. We get a fraction. The answer here might be a little messy, but in fact, the answer is y equals 70 over 11. We then have to go back and plug it into either equation and then find x after using y. But the idea here was to show you how to possibly adjust both equations in order to eliminate one of the variables. So if we wanted to eliminate y instead of x, I might have multiplied the top by negative 7, and I would have multiplied the bottom by 6. Would have been one approach to doing it. Okay? All right, and so this concludes the concept of elimination for solving systems of equations.